The next topic in this unit is graphing sine, cosine, and tangent. The first one we're going to look at is sine. So I'm just going to start with the graph and then talk about the attributes of the graph as we go forward. Okay, so this is a graphical representation of sine. And then in the top corner, I'm also going to include a unit circle. So for sine, we have our unit circle, but we are only looking at the y values, okay? We're not looking at the x values. We're only looking at theta and the y value outputs that extend from those, okay? So if we take a look at this graph, even though maybe this is your first time seeing it, but you can at least use your knowledge from previous graphs in order to analyze it. So for this graph, we are starting at negative pi, and we are going to positive pi. If we look at this, if we were to continue graphing this, the curve would continue like this, right? In the positive direction, we would see it go down, create another concave up moment, and then on the left side, we would see it continue this way, all right? So if you graph it in your calculator or on Desmos and you zoom out, you're gonna see that this is repeating, all right, infinitely, okay? And because of this repetition, this is called a periodic function, all right? It repeats continuously. And for periodic functions, they have something called a period. The period is the length, I wish I'd stop doing that. The period is the length that the function travels before it starts to repeat, all right? For sine, we did a snapshot from negative pi to pi because this is one period of sine, okay? So from negative pi to positive pi, we have one period of sine. Why is it doing that? Which means the period length for sine is going to be 2 pi because we have a pi over here and we have a pi over here, and pi plus pi is 2 pi. So the period is 2 pi. So again, in the description, a period is the length the function travels before repeating. The next question is it an odd or an even function? Well, sine is going to be an odd function because we can see that it has rotational symmetry. About the origin. So if you recall, the definition of an odd function is f of negative x is equal to negative f of x. So that means that outputs will have the opposite value of the opposite inputs, which we'll see when we create this table. Also, we call this oscillating. Sine is an oscillating function because it is repeating. It is a smooth curve. Okay, the next unit is transformations, specifically for trig functions. So if you think back to unit 1, when we did transformations for polynomials, each parent function had a separate transformation table. The same is going to happen for trig functions, okay? So for sine, we take a snapshot of the middle part of this. So our inputs, we're going to start at negative pi, and then we're going to go to pi. So for your key points, you want them to be equally spaced out, okay? So at the center of negative pi and positive pi, we have 0. And then if we continue to split these intervals in half, negative pi, you can think of negative 1. The halfway point between negative 1 and 0 will be negative 1/2, or we can call that negative pi over 2. And then in the positive direction, same thing, we'll call that positive pi over 2. For sine, at negative pi, if we come up to our unit circle, it's negative, so we're opening up down and we're traveling half of a circle, okay? This will have the same answer or the same output as positive pi, okay? So from negative pi, positive pi. So we start at negative pi, we're rotating around our unit circle, and then we stop at pi. That is one period of sine, which is a full revolution, which is going to be 2 pi. So the value for this, sine of negative pi and sine of pi, will have the same output, which is going to be 0, because it's on the x-axis, or the horizontal axis. And then at 0, we can also see that it's going to be 0, because on the unit circle, at 0 degrees, we want the vertical value, which is going to be 0 because it's on the x-axis. Now let's think of sine. So sine of pi over 2. Pi over 2 is going to be at the top, and we only care about the vertical relationship for sine, and that's going to be 1. So sine of pi over 2 is equal to 1. Sorry. Now, if we think of the definition of an odd function, f of negative x is equal to negative f of x. So if I do f of negative pi over 2, this output will be the opposite of whatever positive pi over 2 was, so it'll be negative 1. And then same thing on the unit circle. If we think of sine of negative pi over 2, that is equivalent to sine of 3 pi over 2. And sine of 3 pi over 2 is equal to negative 1. So this table you need to memorize, because you will be using it for trig transformations in the next unit. The domain for sine is all real numbers. And then the range is it's oscillating between negative 1 and positive 1 inclusive. Okay. Cosine, I'll go ahead and draw the sketch, and then we'll talk about it from there. So we'll go here. Whoops, let me fix that. Come up, and then we come back down. So this is a rough sketch of cosine. All right, so cosine, it's called cosine for a reason. It's a co-function of sine, all right? So it's going to share the majority of its attributes with sine. So if you look up top, I should actually include these positions as well. This is going to be negative pi over 2, and then this one is positive pi over 2. And then we have negative 1 and positive 1. If you look at sine, it is exactly the same as cosine, except there is a shift. In cosine, we see that we have a maximum here. Sorry, this is sine. But in cosine, we see a maximum here. All we did was shift sine over pi over 2. So now instead of the maximum being at pi over 2, the maximum is now at 0 for cosine. Okay? So a lot of the attributes that we saw for sine are going to be shared with cosine because it is a cofunction of sine. We're still going from negative pi to positive pi. And then this will be at negative pi over 2. And then this one is at pi over 2. And then we're still using negative 1 and positive 1. So before we talk about the table, the period for cosine is the same as sine. So the period is 2 pi. Now, because we have that shift, this no longer has rotational symmetry. If we were to take this curve and rotate it over, it would not overlap itself, all right? Instead, we have vertical symmetry about the y-axis, so cosine is actually an even function because it has vertical symmetry about the y-axis. Sorry, that's my dog. Vertical symmetry about the y-axis. And then cosine is also an oscillating function, which means it is repeating. All right, so the table for this is going to be very similar. It's just going to have that shift in the y values, pi over 2. So negative pi, we have negative pi over 2, 0, positive pi over 2, and pi. At negative pi over 2, we're at negative 1. At negative pi, we're at negative 1. At negative pi over 2, we're at 0. And then at 0, we're at 1. Pi over 2, we're at 0. And then at pi, we are at negative 1. So when we evaluate these, it's not just negative pi, it's cosine negative pi. And cosine negative pi is equal to cosine of pi, which is equal to negative 1, because it is located on the furthest left side. And that is 1 unit from the center. The domain for cosine, it is going to be all real numbers. And then the range for cosine is oscillating between negative 1 and positive 1. This said graph 2 periods. I just graphed 1 for time's sake. But in the notes that I posted, the key, you'll see the 2 periods in there. All right, the last one I want to look at is tangent. So we'll use a different color. So I'll draw a sketch, and then again, we'll talk about the attributes. Okay. So this is a sketch of tangent, and we'll include a little unit circle here, so we can talk about what those vertical asymptotes are doing. All right, so if we think about tangents, some interesting things are happening here and here. This coordinate is 0, 1. This one is 0, negative 1. And when we evaluate tangent, so if we evaluate tangent of pi over 2, that means we are using y over x, which is 1 over 0, which means it's undefined here, all right? And because it's undefined, that creates a vertical asymptote graphically. Same thing down here if we evaluate tangent. Well, it's 3 pi over 2, but we can also call it negative pi over 2. Those are coterminal. So we'll end up with negative 1 over 0, which again is undefined. So we have 2 vertical asymptotes within one unit circle, all right? So this one will say that it is x equals negative pi over 2 for that vertical asymptote. This vertical asymptote is x equals pi over 2. So right now we are sandwiched here, okay? We start at negative pi over 2 and then we go to pi over 2. So graphically, we're looking at this portion of the unit circle. On the other side, it repeats, right? Because if you remember, tangent is positive here and it's negative here, which is why we see that it's below the x-axis here because the tangent's negative. And then we see that it's above the x-axis here because tangent is positive. And it's negative because the x values are positive in this quadrant, but the y values are negative. Right, so we have a negative output for that. So the period for tangent, instead of 2 pi like cosine and sine, it is going to be 1 pi. So the period is pi. And in the key, there's also a description using sine and cosine, showing why it's also just pi, but this description here is why. It repeats twice within the unit circle, the values do. Like if we look back up here, we see that this quadrant and this quadrant have the same outputs, and this quadrant and this quadrant have the same outputs, okay? If we think about if we think about cosine and sine, the combination of those outputs are different, okay? All right, whether it's odd or even, tangent has rotational symmetry, so it's an odd function. And then it is repeating, so it is technically oscillating. It just doesn't oscillate like cosine and sine. It's just not smooth, but it's still oscillating. Okay, domain and range. So remember, this is just a snapshot. This does continue in both directions for infinity. There's an infinite number of asymptotes. There's an infinite number of increasing curves, okay? Now, as we travel to the right, every single tangent curve is doing this, okay, in between our vertical asymptotes, which means if I read this left to right, I'm technically always increasing. Every single curve is increasing, which means tangent is also considered monotonic. Cosine and sine are not monotonic because they increase and they decrease. Also, another note, at the center here, we have a point of inflection, POI. And that is where concavity is changing. And then if you look at cosine and sine, we also have point of inflections when it crosses the horizontal axis. Okay, so they have an infinite number of point of inflections, infinite number of concave up, concave down. All right, the table for tangent. Now, because the period is only pi, we are sandwiched in between negative pi over 2 and pi over 2. But we are still using 5 key points. Splitting through this is the 0, so we'll have a 0 here. And then halfway between 0 and 1/2 is 1/4. So we'll have pi over 4 and negative pi over 4. At negative pi over 2, we already established that we have 2 vertical asymptotes. Well, there's one at negative pi over 2 and another one at pi over 2. Tangent of 0, that's going to give us 0 because that one is 0 divided by 1. That coordinate point is 0, 1. Sorry, it's 1, 0, so that means it's 0 divided by 1, so we get 0. Tangent of negative pi over 4 and tangent of pi over 4. If we come back here, we evaluated this already. Right here, tangent of pi over 4 is in the first quadrant, and it's root 2 over 2 divided by root 2 over 2, so we get 1. So tangent of pi over 4 is 1. So we'll call this pi over 4. And this will be positive 1. Now, because tangent's an odd function, that means f of negative pi over 4 is going to be equal to negative 1. So this will be negative pi over 4. So again, these are not polynomials, but the attributes as far as like transformations, concavity, all of that, rate of change, it's still going to be the same. Okay, so the fact that it's an odd function, we can still use the definition of an odd function to help with the transformation table that we have. So domain and range. I want to start with the range. Because this is going to negative infinity and positive infinity, that means the range is all real numbers. Or you might see it as negative infinity to positive infinity. The domain is going to be a little different. Because we have vertical asymptotes, there's a couple ways that you can write the domain. So say that we have just a sidebar. Say that we have this. We have a rational function. We'll have a curve here and a curve here. Let's say that the vertical asymptote is x equals 3. Okay. If I wanted to write this domain, I have 2 ways of doing it. I could do x cannot equal 3, which means it equals all values of x except for 3. Or I could write negative infinity to positive 3, non-inclusive, 3 to infinity. Already with one vertical asymptote, this is a more tedious way to write it. Some rational functions have two vertical asymptotes, or 3, 4, it could keep going, which means we'd have to write multiple forms of this, all right? So this is a more efficient way to notate your domain when you have vertical asymptotes. Now for tangent, we have an infinite number of vertical asymptotes, so we have to write it this way. There's no way that we can include every single vertical asymptote by writing it as a union, all right? So we need to exclude the values from our domain that we can't use. So we can use all values in our domain except for, let's start with the first positive vertical asymptote. It's pi over 2. So I can include all values within the domain except for pi over 2. But what about negative pi over 2 or all the other vertical asymptotes? Okay, if I want to include pi over 2, the period for tangent is pi. So that means the vertical asymptotes are separated by pi. So I can do pi over 2 plus pi. But that takes me in the right direction, so that would be 3 pi over 2. So to include an infinite number of vertical asymptotes, we include k, where k is an integer. And another way to write that is k is an integer. So remember, an integer is a value that is not a decimal. Or you can think positive, negative, whole numbers, and 0. Those are your integers. So that way, whatever we plug in for k, whether it's -5, -4, -2, -1, 6, 10, 100, as long as it's a non-decimal number, that will cover every single vertical asymptote infinitely. So I could even plug in k is equal to 1 million. There will be a vertical asymptote there that I can include that excludes this from my domain. All right, hope this helps. Next, we'll be looking at the reciprocals of sine, cosine, and tangent, which are cosecant, secant, and cotangent.